Welcome back. In this video, we are going to once again use PEST to do automated parameter estimation to calibrate this big valley model. But we're going to do things a little differently. In the previous exercise, we used a set of polygons that defined the distribution of hydraulic conductivity in our model, and we applied a separate value of hydraulic conductivity to each of the polygons. And that works well for a lot of cases, and but there's another way to do it which works really well for a lot of models, and it's called pilot points. And with pilot points, instead of using polygons, you define a series of scatter points, these XY point locations, and you assign a hydraulic conductivity to each of these points. And then you use an interpolation algorithm to do two-dimensional spatial interpolation of those hydraulic conductivity values to assign the hydraulic conductivities at each of the cells in your grid. And so you have this kind of a continuous function, or kind of like a 2D surface or a 3D surface, depending how you want to think about it. And then as you adjust the hydraulic conductivity up or down at each of these points, you're basically warping this surface until it produces a distribution, a spatial distribution of hydraulic conductivity that gives you a really good fit between your computed and observed heads. And you know, we would expect our hydraulic conductivity in the aquifer to vary spatially, and so it tends to work pretty well as a parameter, as a parameterization technique. And so in this exercise, we're going to learn how to set up our model inputs for this kind of parameterization, and then run PEST and ModFlow to calibrate using pilot points. All right, so again, there's a set of files that I imported and it was a pilotpoints.zip. Unzip that, and we're going to import this model. And again, it's another version of this big valley model. And what we're going to do, the first thing we need to do is create a set of pilot points. And you can do that in a couple of ways. You could go into the 2D scatter point module, create a new 2D scatter point set. I'll go right here, new 2D scatter point set, and then you could start clicking points. I'm doing them here on the side so you can see them. And you could create points, and then you could select the points and then edit their values. And that way manually create a distribution of pilot points. And that works pretty well. Another way to do that, and that's actually my preferred method, is to interactively, place your points. Another method is to uniformly distribute your points, and that's what we're going to do in this exercise. We're going to create a grid and then interpolate those, use that grid to generate a grid of scatter points. And so here's what you do. You select new grid frame, and then I'm going to click on the grid frame and select fit to active coverage. Whoops, maybe I don't have the right active coverage. Here we go. There. Now that puts that grid frame around my model. And then we are going to say map to 2D grid. We only need a 2D grid here, not a 3D grid. And then in the X direction, we're going to do 5 cells. In the Y direction, we're going to do 10 cells. And that should be everything we need. So it creates this grid in the background. And then we are going to right click on this grid right up here and select convert to 2D scatter points, and we'll call this HK for our scatter point set name. And what it does is it creates a scatter point set with a scatter point at the center of each of these grid cell locations. So I'm going to turn that grid off for now. In fact, we could delete that at this point if we wanted to. And so that's just a way to uniformly distribute a set of points throughout your domain using a grid. Sometimes this works really well, sometimes it doesn't. In this particular case, it works really well, and so it's a nice way to do it. Now, another thing we need to do is we need to assign the some values to these scatter points. If you click on them, you'll see they have a default value. F is the data set value, and let's see. Let me get rid of that grid so I don't. Whoops. I'm going to get rid of my grid so I don't keep confusing that with my scatter point set. So the pilot point values, the hydraulic connectivity values, come from the data set values associated with our scatter point set. And so we have a default data set, but the values, they're all 0. So we could come in here and enter 0.5 and then just copy that down by double clicking on that little rectangle like you do in Excel. And that's one way to do that. Another way is you can unlock your scatter points, and then using the select point tool you could just drag a box and select them and edit it right up here. But either way works. So now they all have a starting value of 0.5. And the next step, once we've created our scatter points, is to go into our list of parameters. Now this model has already been parameterized. And by the way, let me back up a little bit. So if you look at your HK array, the entire grid has a key value of -30. And so when you're doing pilot points and you want it to apply to the entire hydraulic connectivity array, and by the way, you could use pilot points on anything that varies spatially, so you could do it on recharge as well. But we're doing hydraulic connectivity. So we've set the entire grid to be a key value of -30. And then we are going to go into the parameters dialog and we're going to use this little button on the side, pull down button. We're going to say instead of using a constant, we're going to use pilot points. And then we're going to click this top part of it. And here, if you happen to have multiple scatter point sets and data sets, you could select them here, but we only have one, so it picks it. It also defines your interpolation options. And a lot of times you want to turn on log interpolation. We're just going to leave it at the defaults here. And click OK. And OK. And then another thing we're going to do is we're going to do mod flow parameter estimation. And these are the options associated with parameter estimation. And there's a max number of iterations, which is set to 20. We're going to change that to 5 because with this particular model, after 5 iterations, it has a really low error, but it just keeps on running PEST. And in the interest of saving ourselves a little time, we're going to tell it to stop after 5 iterations. And so let's go. I'm going to do file save as here. And we're going to call this PEST _ ppt.gpr. And hopefully we've got everything set up. And we run PEST. The first time it runs, we've got an error of 2952. Now notice each of those pilot points becomes a separate parameter value. So we have 50. We have a 5x10 grid that gave us 50 scatter points. So we have 50 pilot points and then 3 recharge values. And so it's going to take a little longer than the last one we did. but not too bad. So now it's made one iteration. It's modified both the recharge and the hydraulic conductivity values. And you can see here, this is the number of runs here is the number of runs within an iteration. So there are 52, 53 parameters. And so it's running at once. In the PEST iteration, it's running mod flow once for each of the parameters. And it uses all that information to get a gradient that it then uses to change the parameters for the next iteration. And over here we see the sum of the error, which is the sum of the squared weighted residuals versus PEST iteration. And you can see after 3 iterations we're all the way down to 40. Now why do I say 3 iterations? Over here it says 4. Well, iteration 1 is just your initial values. So it's actually made 4 change. We're on the 5th iteration technically, but it's made 4 sets of changes at this point. And now that's flattening out. We're down to 9 as our total model error, which is almost nothing. And let's see what we get now. 2.35, which is means there's almost no error at all at this point. And that reached our maximum number of iterations, so we're going to close and then read in. There's our solution. And let's scroll down and look at our observation wells. Now they're all in the green. You can just see a little tiny bar. You look over here, these are the residuals. They're almost nothing. Let's look at our properties for our solution. Yeah, all the way across the board, there's just almost no error whatsoever. And it doesn't always happen this way. Again, this is a really simple model. It allows us to get a really good result when we calibrate it. But the pilot point calibration gave us a better or a lower error than we got with the zone-based calibration, although they're both very good. All right, what do we do now? Now that we've got our optimal solution, we can, one question we may have is, well, we now have this spatially varying hydraulic conductivity defined by these pilot points. What does that look like? And so if we go into the parameters dialog and we select import optimal values, what it did is it reads in our optimal recharge values, and it imported our optimal hydraulic conductivity values at each of these pilot points. And you can see we have a new data set up here on the scatter point set. And if we look at view values, here are the optimal values it found at each of those pilot points. And then if you click on the HK array, at this point it will, if you double click on that, that's still minus 30, but when you click on it to contour it, GMS is smart enough that it automatically interpolates from your scatter points. It knows that you're using pilot points, so it interpolates these values. So we have this one's a little higher here, 2.4. The rest of these are pretty small and very spatially, so that's how our hydraulic conductivities ended up being distributed in order to give us the best fit there. Now the last thing we want to illustrate is in some cases you might have a pump test where you've done a field measurement of hydraulic conductivity, and you may wish to input the results of that pump test as a fixed K value and allow and use that in your interpolation of your pilot points. So in other words, you can have selected pilot points where the hydraulic conductivity doesn't vary. It stays at the initial value you've defined. And so let's illustrate how to do this. We're going to go back here and we're going to make sure, we're going to go select this scatter point set and make sure our HK30 set of pilot points is selected, or excuse me, a data set, and then we're going to use the create point tool, And let's see, let me turn off the observation wells right now. And you can see we have a well right here. So we're going to click there. And let's see, then we're going to click on this well. We're going to click on each of our 3 well locations, assuming that's where we did our pump test. All right. And then we are going to let's see, we are going to, let's turn this grid off for a second so we can see these points. And we are now going to edit the values of those points we've set up. So I'm going to unlock my scatter point so I can edit the values. And I'm going to click right there. And I'm going to, this one has a value of 1. And then this one right here has a value of 5. And then this one over here has a value. Wait a minute, this one is supposed to be 5. I did them backwards. That one's 5. And this one is supposed to be 0.1 according to the tutorial. Oh, another thing I need to do is I'm going to double click on that and I'm going to make it a fixed pilot point. And double click on that and double click on that. I could have multi-selected them. So there's one of the properties of a scatter point is you can mark it as a fixed pilot point. All right, so now we are going to run PEST again and see what happens. And it's going to use the same pilot points we had before, and but it has 3 additional points now. So now you'll see we have 53 pilot points instead of 50. And let's see if it can. It's not necessarily going to improve by adding those fixed pilot points. We've basically added a constraint. And under these circumstances, it may not give us a lower error, but it does make the hydraulic conductivity match what we've observed in the field. And so we'll let that iterate for a minute. So again, you know, we used a grid to set these points up. You know, another option is you just go in and start clicking and creating the points wherever you want. Generally, you want to put your pilot points between your observation wells, not right on top of your observation wells. And you got to be careful. A lot of times when you do pilot points, you can get carried away and create too many points. And the more points you have, the longer it takes to run your model. So you want to use as few points as you can to generate a reasonable surface that gives you a low residual error, but not so many that it takes forever to run. Now, looking at our results here, after our 5 iterations, we have error of 2.9. So we ended up getting about the same error, very low error. This is about what we had before. But now this interpolation is ensures that the hydraulic conductivity at those 3 locations that we specified where the pump tests were made is exactly equal to what we measured in the field using the pump test. So it gives it a little bit of extra twist. Oh, by the way, it looks like we got even lower. We got 0.8. I'll be darned. Both of those are really small, so I'm not sure that's terribly significant, but we did get a really good rate once again. And let's look at the properties. You can see these errors are all almost 0. Sum of squared weighted residual 0.8. That's almost nothing. And so anyway, that's how you use pilot points. Very easy to use. Again, you create a set of scatter points, assign a starting value for your hydraulic conductivity to each of the scatter points, mark your hydraulic conductivity array with a single key value, and then link those together, and off you go. Works great. Really a nice tool to use when you're trying to calibrate your model.